In this lesson, we're going to take a look at some basic ideas behind matrices and matrix operations. This is going to help to prepare us for our unit on fractals. First of all, a matrix is simply a rectangular arrangement of numbers. So it's like a table with rows and columns. And we talk about the dimensions of a matrix based on the number of rows and columns. So if we're talking about a 3 by 5 matrix, a 3 by 5 matrix has 3 rows and 5 columns. Sometimes a matrix will have the same number of rows and the same number of columns. So maybe a 3 by 3 matrix or a 5 by 5 matrix. If that's the case, we have what is known as a square matrix. Let's take a look at some matrix operations. To begin, let's talk about adding and subtracting matrices. To add or subtract matrices, they must have the same dimensions. So for example, the matrix here on the left, matrix A, is a 2-row by 3-column matrix, and matrix B is also a 2-row by 3-column matrix. So in order to find the sum of matrix A and matrix B, I simply add the corresponding elements. So 3 plus 0 is 3, 1 plus 4 is 5, negative 1 plus negative 2 is negative 3, and so on. Notice here I'm adding the second row first column with the second row first column, and notice I'm storing the sum in the second row first column. So adding matrices together is pretty straightforward. And so is subtracting. We just have to subtract the corresponding elements. 0 subtract 3 would be negative 3. 4 subtract 1. Negative 2 subtract negative 1. 1 subtract 0, and so on. But what about adding matrix A with matrix C? Matrix C here is a 3 by 2 matrix. I could start adding the 3 with the 1 and the 1 with the 0, but then what would I do with this negative 1? It simply wouldn't work. So here it's not possible, or we could say it's not defined. Remember, in order to add or subtract two matrices, they must have the same dimensions. Let's take a look at something called scalar multiplication for matrices. Here I've got matrix C and I want to find 4 times matrix C. Well, just as you might suspect, what we're going to do is take every number in the matrix and multiply it by the scalar. In other words, it's kind of like the distributive property. So I would take 4 times each of these items or each of these elements in the matrix. So 4 times 1, 4 times 0, 4 times negative 3, and so on. Scalar multiplication is pretty straightforward. Finally, let's take a look at matrix multiplication. In matrix multiplication, we're going to multiply rows by columns. And just like not all matrices could be added, not all matrices can be multiplied. In order for matrix multiplication to be defined, the number of columns in the first matrix must equal the number of rows in the second matrix. So let's see what this means as a practical example. Let's say we have a 2 by 5 matrix and we have a 5 by 1 matrix. This matrix multiplication would work because these two numbers here are the same. The number of columns in the first matrix is equal to the number of rows in the second matrix. Notice we have numbers here on the outside. These outside numbers would be the dimensions of our answer. So once we're done multiplying our matrices together, we're going to have a 2 by 1 matrix. So the dimensions of the product can be found by using the outside numbers here, the number of rows in the first matrix and the number of columns in the second matrix. Just to make sure we are clear on this, let's take a look at a couple examples. Here we have a 5 by 3 matrix that we'd like to multiply by a 3 by 2 matrix. First of all, let's see if this will work. Well, these two numbers are the same. The number of columns in the first matrix is equal to the number of rows in the second matrix. And our final product is going to have dimensions of 5 by 2. What if we multiplied the matrices in the other order and did matrix B times matrix A? Would that work? Well, matrix B is a 3 by 2 matrix, matrix A is a 5 by 3 matrix, and because the inside numbers here, the number of columns in the first matrix, is not equal to the number of rows in the second matrix, this is not defined. It will not work. So matrix multiplication is not commutative. Finally, let's actually take a look at some matrix multiplication and work out an example. Here I have a 2 by 3 matrix, and this is a 3 by 2 matrix. 2 rows, 3 columns, 3 rows, 2 columns. Notice we have numbers on the inside here that are the same. The number of columns in the first matrix is equal to the number of rows in the second matrix. And I know that the dimensions of my answer are going to be 2 by 2. And what I like to do is create a big matrix and create blanks to fill in as I do my matrix multiplication. Notice we have 4 elements here. This is the first row and first column of our answer, and to get that, we're going to multiply the first row times the first column. So that means we would have 0 times 1, so first item times first item, plus 4 times negative 3, second item times second item, plus negative 2 times 0. Next, we're going to take the first row times the second column, and we'll store the results in the first row, second column. So we'll have 0 times 0, which is 0, plus 4 times 4, plus negative 2 times 9. Now I need to fill in the second row. To do that, I'll start by taking the second row times the first column. So initially here I'll have 1 times 1 plus 7 times negative 3 plus 6 times 0. Then to get the final row and column, the second row, second column, I'm going to multiply the second row times the second column. And for that, I'll have 1 times 0 plus 7 times 4 plus 6 times 9. And to finish up our answer for this, we just need to do a little bit of arithmetic. So we'd have 0 plus negative 12 plus 0, that's going to be negative 12. Here I'd have 0 plus 16 plus negative 18, that's going to be negative 2. Here I'm going to have 1 plus negative 21 plus 0, so that's going to be negative 20. And here I'm going to have 0 plus 28 plus 54, which means that the last element in this matrix is going to be 82. For this particular lesson, we don't have a survey, but you do have a brief worksheet.